So welcome everyone to the ATN seminar. Today's speaker is Iván Rasskin, who will be talking about polytopal crystallographic sphere packings for geometric knot theory and fractal modeling. Iván, the floor is yours.
Okay, thanks. Thank you, the organizers, for the invitation. So I'm going to talk about sphere packings, a family of sphere packings that are called crystallographic sphere packings. And inside, we're going to check a family of polytopal crystallographic sphere packings and two applications of this family in knot theory and fractal modeling. Let me check. So this is the menu for today. So we are going to see an introduction of the geometry of sphere packings, what are going to be the geometry that we're going to use for manipulate these objects. Then we're going to introduce the definition of polytopal crystallographic sphere packings, the main object that we are going to use. And we're going to see at the end the two applications in knot theory and fractal structures. So we're going to work on the spherical model, so on the sphere in dimension D, and we can project a spherical cap into the Euclidean space of same dimension. And we're going to compactify this space. So we're going to add the infinity as a point. And we're going to say that a sphere in the Euclidean space, in the compactified space, is just the image of a spherical cap under the stereographic projection. So it's going to be an oriented sphere. So we're going to have an interior, so one side of the sphere. So depending on the relative position between the spherical cap and the North Pole, there are three types of spheres. So we can have a regular ball, so with positive radius. If the North Pole touch the boundary of the spherical cap, we will have a half space, so the radius is infinite. And if in the third case, if the North Pole is inside the spherical cap, then when we project, we have the complementary of a regular ball. So it's usually called a hollow sphere. So we can model in this with a negative radius. So a sphere packing is dense if it fills almost all the space. So for example, if this is a sphere packing that is not dense, but we can fill the space by adding more spheres. For example, here we add a sphere with negative radius. We'll have less and less space, empty space. And if we continue with this procedure, we can get an infinitely sphere packing that is dense. So for constructing this dense packing, we can use reflection groups. So we can, if we use just Euclidean reflections, we combine two Euclidean reflections, we can already get an infinite sphere packing, but it's not dense. If we change the position of these reflections, these mirrors, we can get something more compact. If we add a third reflection and a fourth reflection, we can get this infinite packing that fill almost all the space, but we have still these empty spaces. And then we can add another reflection that is called a spherical reflection or hyperbolic reflection, which is a reflection on a spherical mirror. It's also called inversions. So these inversions preserves angles, change the volume, and has the good property that reflects sphere packings to sphere packings. It also fixes spheres orthogonal to the mirror. Parallel mirrors generate infinite sphere packings. They can generate infinite inversions. This inversion generates the group of Mobius transformation, also called the conformal transformations, that preserves locally the angles. So if we add now these spherical reflections to the same setting that we had before, we can use this mirror now to fill more densely the space. Assistance, for example, if we start from this configuration of 4 pair with tangent circles, oriented circles, we can use these inversions. For example, we can pick an inversion that fixes 3 circles, so it's going to be orthogonal to a triple. If we combine two different, when we apply one inversion, the 3 orthogonal circles, they're going to be fixed, and the remaining one, is gonna fill the empty space in this direction. Now, if we add a second spherical mirror and we combine these two infinitely, we will have these two infinite branches. We add a third one and we apply the third inversion. We have this infinite action. We will gonna fill almost all the space. And if we want to get something dense, we need to add a fourth spherical mirror. So the action of these four spherical mirrors for a spherical reflection will give us the polynomial circle packing, which is a dense circle packing. So we're gonna fill the space densely. So this object is very common. We're gonna look some generalizations of this polynomial circle packing. So for this, we're gonna use polytopes. So a D polytope is just a convex hull of endpoints in RD. So we have to pick more than D plus 1 points in general position. So it generalizes the notion of polygon or polyhedron. So a 2 polytope is just a convex polygon, a 3 polytope is just a convex polyhedron. And for polytope, we cannot draw it. We can draw a projection, for example, a Schlegel projection of the skeleton. So polytopes are geometric objects, but they are also combinatorial objects. So we can use the combinatorial structure of a polytope if we select the cells of this complex cell, and we can use the phase lattice structure, so that is a poset. It's just the collection of all the faces, all dimensional faces, with the inclusion relation. A flag of a polytope is just a chain of faces that start from the bottom and raise to the top. So a polytope is regular if its symmetric group acts transitively on its flags. So we have two flags, two chains, and there is a symmetry that move one into the other. For example, this polytope is not regular because there is a square face. So the change that pass from this square face is not going to be the image of any other flag under asymmetry. So what are the regular polytopes in every dimension? This is very well known. So in dimension 2, all the 2 polytopes admits a regular realization. So there are infinitely many. In dimension 3, there are only 5, the famous Platonic solids: the trahedron, the octahedron, the cube, the icosahedron, and the dodecahedron. In dimension 4, there are 6 regular polytopes. So we have the generalization of the previous one, the hypertetrahedron, hyperoctahedron, until the hyperdodecahedron. And we have also an extra one, the 24 cell. In dimension 5 and above, it is well known that there are only 3 regular polytopes. So the generalization of tetrahedron, octahedron, and cube. So this is the complete list of regular polytopes in every dimension. So how we are going to use this polytope for construct the sphere packing? So polytope in dimension d plus 1, it's described if every edge is tangent to the unit sphere in dimension d. So this polytope here, these 3 polytopes, is described because every edge touch the sphere, the unit sphere. A polytope that admits a described realization is called describable. So that we can deform it to get an described realization. So Brightwell and Scheinerman proved that every 3 polytope is describable, so every polyhedron can be realized with every edge touching the unit sphere. It is known also that there are non-describable D polytopes in dimension 4 and above. Are examples of non-describable polytopes. But the regular family, every regular polytope is describable. So we can place a sphere centered in the barycenter. We can grow the sphere until it touches one of the edges. By the symmetry of the regular polytopes, they're going to touch every edge. So how we construct a sphere packing from polytopes. So we're going to use a projection, and then we call arrangement projection, that transforms polytopes in dimension d+1 into a sphere arrangement, not packings in general, so a collection of spheres in dimension d. So we are going to decrease the dimension by 1. So we take a polytope whose vertices are outside the unit sphere. We're going to place a light on each vertex of the polytope, and we're going to illuminate the unit sphere from this light. So this is the illuminated region corresponding to the light placed at this vertex. These illuminated region are spherical caps that we can project using the stereographic projection, and we get this collection of spheres in dimension d. So we start from in this example, we start from a 3 polytope, a polytope in dimension 3, and we get a collection of circles in dimension 2. So if we look at one edge, if the edge is cutting transversally the unit sphere, then the illuminated regions, the spheres that corresponds to the vertices, they're going to be disjoint. In the other case, if the edge is avoiding the sphere, then the illuminated regions, they're going to overlap. So in the middle case, if the edge is exactly touching the sphere, is tangent to the sphere, then the corresponding spheres, they're going to be tangent. And this is the case that we are going to be interested. So we're going to say that the sphere packing is polytopal if it's the image of a net-scribe polytope under the arrangement projection. So we're going to start from a polytope where every edge is tangent to the sphere, and we're going to get a collection of spheres that is going to be a packing. We're going to have more structure than just a packing. The structure of the polytope is going to be sent to the sphere packing. For example, the vertices of the polytope encodes the spheres, no? And the edges encodes the tangency relation. If there is an edge between two vertices, that means that the two spheres are going to be tangent. But also the faces, well, with these two, we can define a contact graph. The contact graph of the sphere packing is going to be the same as the graph of the polyhedron. But the faces also, well, in high dimension, the facets, if we take the intersection of the facet with the unit sphere, they're going to give us the spherical reflection that we call the dual spheres. These are if we apply the reflection on this dual sphere to the initial packing, we're going to get in the case, for example, for the tetrahedron, we get the polynomial circle packing. So we get a crystallographic sphere packing from this construction. So in dimension 2, the union of infinite reflection through the dual spheres is always a dense packing. So if we change here the polyhedron, for example, we start from a cube, we take the intersection with the faces that give us the dual mirror. We apply the reflection through the dual mirrors, and we're going to obtain an infinite circle packing that is dense, coming from the cube. This is for a pentagonal pyramid. We get the same. What happens in higher dimension? So if we start from, for example, a hypertetrahedron, so we can realize with every edge tangent to the sphere, when we project from this fourth dimension, we get something in 3D. So we get a collection of spheres in 3D dimension. And when we reflect through the dual spheres, we get something that is also a sphere packing. It's called actually the Apollonian sphere packing. So it works also for the case of the hypertetrahedron. It works also for the hypercube, for example. If we start again from the projection and we do the reflection through the dual mirrors, we get something that is also a sphere packing. So the spheres do not overlap. But actually, this is not true for every case in 4D. For example, if we start from the hypericosahedron, the generalization of the icosahedron in dimension 4, we do the same game. So we reflect through the dual mirrors, and actually we get some overlapping here. So it's going to depend on the dihedral angles of the scribe realization here. So we're going to say that the polytope is going to be crystallographic if the union of this infinite inversion give us a packing, so there is no overlapping. So in this case, for example, the hypericosahedron is not crystallographic. And the hypercube is crystallographic. So these crystallographic polytopes, we have a theorem of Kontorovich and Nakamura that introduced the notion of crystallographic sphere packings. Using a result of hyperbolic polytopes, they can show that actually crystallographic polytopes exist only in dimension 3, between 3 and 996. And what about regular crystallographic polytopes? So if we look at the family of regular polytopes, actually, in one of my work, proved that there are only exactly 11 regular crystallographic polytopes. So in dimension 3, all of them are crystallographic. In dimension 4, we saw that the hypericosahedron is not crystallographic, but the rest of the regular 4 polytopes, so we have 6, no? So there is one that is not crystallographic, but the other 5, they are crystallographic. So when we do this reflection, we get something that is a sphere packing. There is no overlapping. So we get 10, and there is one more. It's in dimension 6, is the generalization of the hyperoctahedron in dimension 6. This one, when we do this reflection, we get something again that is a sphere packing. And that's it. In other dimension, we take a regular polytope. When we do this reflection, we will have the overlapping phenomena. So these are the objects that we're going to manipulate. So in geometric knot theory, we're going to look at this problem. So a knot, what is a knot? Is just a closed simple curve in R3, compactified. So these are, we're going to look this up to isotopy. So this is a bunch of examples of classic knots. And link is just a disjoint collection of knots. We're going to look at a specific representation of knots. It's called necklace representation of a knot or link, just a sphere packing that contains a polygonal representation of the link. So we can embed the knot inside the sphere packing. So this is a necklace representation of the trefoil knot. And this one is a necklace representation of the Borromean link. So this necklace representation have been useful for hyperbolic geometry, for example, or computing the hyperbolic gas volume of 3 manifolds. Also, they are useful for molecular biology, for modeling molecules. Also, we can use them for defining the formations of knots, the formations that preserve the topology and avoids intersections. If we want to define such a deformation, we can use this necklace representation, apply a Mobius transformation that is going to preserve this sphere packing. The sphere packing is going to protect the topology and the self-intersection of the knot. So there is a natural question about this construction is we have a given knot. What are the minimum number of spheres that we need to construct a necklace representation for this knot up to isotopy? So for example, here we have 3 necklace representations of the same knot, the trefoil knot. So this is an open question. The minimum number of spheres for the trefoil knot is not known. So this is actually an invariant that introduced by Mayara. It's called the ball number. It's the minimum number of spheres needed for construct a necklace representation of a link. What is known is, for example, for the trivial knot, just the circle, we need 3 spheres. We need to, with 3 spheres, we can construct a triangle that makes the necklace representation. Mayara proved that the ball number of the uplink is actually exactly 8. And this is the only link that we know exactly what is the ball number. Mayara and Osiro proved that actually for the trefoil knot, so they gave a construction with 12 spheres, is the construction that we saw here. And they managed to prove that with 8 spheres, no matter the size of the position, we cannot construct a trefoil knot. So it's still open. If with 10, 11, and 9, we don't know if we can construct this trefoil knot. So they conjecture that their construction is optimal. So in my thesis with Ramírez Alfonsín, we proved we gave an algorithm for construct this necklace representation in terms of the crossing number, so the minimal number of crossings. So, and we give an algorithm for construct this necklace representation. We start from a diagram with n crossings, and the output of this algorithm give us a sphere packing with 5n spheres, 5 times the number of crossings. And inside this sphere packing, we can use the contact graph, and we can find Hamiltonian cycle that passes through every sphere, and that will give us the necklace representation of the given knot or link. So with this, we can give an upper bound of the bond number in terms of the crossing number, a linear upper bound. But actually, we think that this upper bound is not sharp. Actually, we think that for alternating links, the bond number should be 4 times the crossing number. And the idea behind is that for construct a crossing, we need 4 spheres. And the idea is that we have to close these crossings when it's alternating for construct something with 4 times the number of crossings. And the alternating property will force we cannot improve this constraint of 4 spheres per crossing. And we managed to improve this upper bound to the conjecture one for rational links. So we changed the method for constructing these necklace representations for rational links. And for that, we used these crystallographic sphere packings. So if we use these sphere packings where we we reflect through the dual spheres and we fill the space, inside these sphere packings, we can find chains that contain a given knot. For example, here, these are 3 changes that contains a necklace representation of the trefoil knot. So actually, we can do this for every knot or link. So we prove that every link admits a necklace representation in the 5 regular crystallographic sphere packings. For proving this, we just look at some structure that is inside these sphere packings that actually allow us to draw the knot like in a regular grid, a square grid of a triangular grid, and inside we can embed a braid. And there is a famous theorem from Alexander that says that every link can be constructed from closing a braid. So every braid is contained in these sphere packings. So we can prove that every link is contained in these regular crystallographic sphere packings. And we have the existence of this necklace representation, but actually we can use it to improve the upper bound. So it's going to be more optimal than the previous upper bound, the previous algorithm. So this is the first algorithm where we construct the necklace representation of a knot with 4 crossings. And we use 5 times the number of crossings for construct the sphere packing. With this second method using the crystallographic sphere packing, actually we use the hyperoctahedral one. We can decrease the number of spheres. We can use exactly 4 times the number of crossings. So this is all for the knot theories, and now I'm going to talk about the application for fractal structures. So this is a project in collaboration with a team from Dijon in France. And these lacunar fractal structures, they are objects that we're going to make like this kind of holes with a fractal system that may allow us to get a solid object and make it lighter. So it's going to be useful for industrial purpose. So it comes from very well known, the IFS system, so iterative function system, that introduced by Hutchinson in 81. So it's just a collection of functions that are contractive. And we apply again this function infinitely, and we look at the limit set. For example, we can get the Sierpinski triangle from a EFS by defining starting from a triangle and defining three transformations that are going to be three homotopy that move this triangle to this triangle here. So this is the first transformation. The second transformation moves this triangle to the second one. And the third transformation move the initial triangle to the upper one. And repeating this process, we get at the end this fractal. And this is very connected with the other fractal that we manipulated before. Actually, the Apollonian circle packing is topologically equivalent to the Sierpinski triangle. We can just modify its circle to a triangle, and we get exactly the same topology. So the BCIFS model introduced by Sokolov, Wettig, Gentil, and Mishkinin in 2015 generalized extended this IFS model by using also iterative function, but it's going to be encoded by an automata. We are going to define some equations that will allow us to control the shape of the final fractal. So in this model, we need three objects. We need the automaton for defining how the primitive is going to be subdivided. So here we're going to define two kinds of operators. So the subdivision operator that define how the cells are connected. So we have a two cell that by this boundary operator connects to this one cell, these edges, and we have also a boundary operator that connects this one cell into a vertex. We have also subdivision operators that says how one cell is going to be subdivided in two different cells. For example, here, this edge is going to be subdivided in also two different cells, but we have two different types of edges here. Here we're going to get one edge, this edge is going to be transformed into a Bézier curve, and this edge is going to be transformed into something that is disconnected. Actually, it's a counter curve. This is what we saw here before. So this edge is going to be a Bézier curve, and this edge is going to be a counter curve. And these connectivity properties are going to be defined by this equation that are called incidence constraint and adjacency constraint that says how these operators are related. It's just so this incidence constraint says if we apply, for example, the green one says if we apply a subdivision and then we go to a boundary operator, it's the same that first doing the boundary operator and then applying a subdivision. So with this constraint, we're going to impose some properties on the connectivity of the final fractal. And by solving this equation, we get something with freedom, that this degree of freedom will allow us to define some control points in the final shape that they are going to deform the boundary and also the shape of the holes. So this is the BCIFS model, and we're going to apply this for modeling crystallographic circle packing, because the problem here is that defining this incident constraint and this constraint can be complex to define. We don't know the final shape. And the good thing of modeling these circle packings is that we can use the polytope that is behind to defining this equation automatically. So the idea is that we are going to look at not at the circles, we're going to look at the complementary of the circles, and we're going to apply the same process as before. So we're going to reflect the spheres that now they're going to be holes. So we're going to reflect the holes using these inversions. and that give us a lacunar fractal structure. And we're going to try to define this BCIFS model for these objects. When we extract this final structure, at the end, we're going to be able to deform the final shape using the control points. So the idea behind is that the structure of the polytope can encode the cells of the primitive. So for example, a face of the initial polytope will give us a face of the fractal. A vertex of the fractal is going to be encoded by an edge, for example. That's why we call this vertex the vertex 1, 3, which corresponds to the edge 1, 3. An edge of this fractal corresponds to a pair of vertex, the vertex 1, and a face 1, 2, 3. So we can define the states of the automaton that we need, but using just the combinatorial structure of the polytope. We can also define how the subdivisions operator works using also the combinatorial structure of the polyhedron. So from that, we can define automatically the automaton. And also we can define two algorithms for computing all the equations that we need, the incidence constraint and the adjacency constraints, for defining our lacunar fractal structure. And all of these elements are defining in terms of the polyhedron. We can then also glue different lacunar fractal polygons. So if we attach to different polygons that we want to subdivide with different methods, we can attach different polyhedron. There is a property that from a vertex, if there is the same degree in both sides, then the subdivision is going to match and we get something that is continuous. So we can define different polyhedral methods for each cell. And at the end, we can also deform it using this degree of freedom. So there is I can show you some of the implementation made by Boris Bordeaux from the it works or not? So the idea is that we're going to select, for example, from Blender just a polyhedron, any arbitrary polyhedron, and from this polyhedron we need to compute the described realization. Maybe it's a bit fast. From this described realization, where every edge is tangent the sphere, we can get the circles and the dual circles to construct the fractal. And we're going to look at the complementary. The complementary is going to be the primitive of the fractal structure. And this is going to be the inversions that we're going to apply iteratively. We're going to extract this fractal to the fractal made by the sphere packing. We can select, for example, a face of this polyhedron. And when we can extract the BCIFS model of this fractal to deform the final object. So we get something that is topologically equivalent to the circles, but here we have these control points that can deform the boundaries and also deform the shape of the holes. Yeah, exactly. Yeah, and here are the iterations. Some perspective is we are working on changing the methods for the subdivision. If we apply, for example, this circle packing, by applying these reflections through the dual mirrors, we get this crystallographic sphere packing, as we saw in this talk. But we can change, for example, the rules and changing, okay, instead of filling the empty spaces, we can also, for example, follow the barycentric subdivision. So we're going to break also the edges. For example, here, in the first step, we start from the tetrahedron. In the second step, we're going to break also the edges. In this way, we get a different sphere packing. So in 3D, so it's going to work. Every subdivision is going to be tangent to the sphere. In 4D, it's not clear, but we have some hopes that it's going to work. This will give us a method for defining this fractal structure in 3D that we can also use for this modeling in the industry with this object has good properties for rigidity, for example. These are examples of these methods, the barycentric subdivision of coming from a hypertetrahedron, and this one is from a hypercube. And these are the references. So in these first 4 papers are the classification of the crystallographic sphere packing and the application in the geometric knot theory. And in the last paper that we submitted is the application in the lacunar fractal structure. And that's it. Thanks for your attention.
Thank you very much, Iván. Let's all briefly unmute and give Iván a round of applause. So very, very interesting talk. I like the visuals. I mean, who doesn't like fractals, right? Do we have already some questions from the audience? If not, I'm going to start with a very naive or maybe almost trivial one. But I mean, I come more from this data science / machine learning world, and so when I hear about problems like these, I always wonder. You mentioned that there are some instances where you only have, let's say, 11, right, of instances, but are there instances where you could create, well, I guess through barycentric subdivision, right, where you could create more of these instances so that you can potentially construct a big data set that a bigger machine learning model could learn characteristics from and maybe help you kind of stumble over new properties. I'm sorry, this is a little bit random, but I kind of got excited about this idea of using that to kickstart mathematical discoveries.
Yeah, that's a very good point. I've never thought about this, but the problem in higher dimension is how to define these edge scribe realizations. There is no method that works well in higher dimension, so it's a nonlinear problem. But yeah, maybe there is something that can be done in this direction. So maybe using the 3D cases that is already solved, maybe it can be a good way to construct a large amount of examples that a machine learning model can. I don't know. I have to think about it.
No, so same here. I mean, this just came up for me because I'm kind of interested in exploring this intersection of where maybe like having access to large quantities of data could actually help in giving you hypotheses for things to prove. That is one of my dream projects at the moment, like generating conjectures or helping others generate conjectures based on data. So not having the model do the work for you, but the model just serving as some kind of intuition pump that gives you ideas of what could work. But no, sorry, that was maybe a little bit too much tangential. Do we have other questions from the audience? I think Henry has a question, right?
Yeah, I'll ask a question. So you described some nice results, upper bounding the the ball numbers of knots? Are there reasonable techniques for lower bounding the ball numbers?
Well, there are trivial lower bounds like the crossing number, for example, or the stick number, because these realizations are actually polygonal realizations. But maybe there are some hope to. There is a lower bound for just the truthful case that is not trivial. So they use like trigonometric arguments to prove that the truthful knot cannot be realized with 8 spheres. So maybe there is a way to generalize this method for other knots. Can be a clue.
Thanks.
You're welcome.
Interesting. Do we have some other questions from the audience? Let's see whether I can see some raised hands. If not, maybe let me continue with the more with the less tangential question. Help maybe. So what how do you have some ideas of how to extend this? I mean, you mentioned that it's harder in higher dimensions, but is there some are there some avenues where you would say, okay, this is definitely fruitful and the way to go?
You mean for defining edge scribe realization or?
Yeah, for instance, yeah.
Well, for the regular case, it's feasible. So some polytopes with a lot of symmetry can be helpful for that. So there are, I think there are uniform polytopes. These are just some very symmetric but not regular. So they are less symmetric than regular polytopes. But this is also a large family. I think maybe those one can be also can be easy to prove that they are also scribable, because the symmetry group acts transitively on the vertices, I think. So when you have just one edges, you can move this edge symmetries. But I think, for example, the list of all uniform polytopes in 4D is quite big, and there is not a complete list in higher dimension, as far as I know.
Yeah, very interesting.
Yeah.
It's super fascinating. It's something completely new for me, so I'm really excited about this. Do we have some other questions?
I have a question. Is there a limit, like from the application point of view? Is it possible maybe that they want to control how much you take out? Because maybe the structure is too light. So you want, what would be, I think the question would be like, from an engineering point of view, I can see how you can be doing it. Like you just do less iteration. But is there a mathematical way to, control it and say, okay, let's say, I don't want a packing, I want a almost packing, or it's a little bit of a weird question. So
no, it's very interesting question. Actually, this how the size of these holes are increasing are governed by the Hausdorff dimension of the limit set.
Oh, okay.
So you can start from a initial configuration. How the weight of the iterations is decreasing is going to be governed by a constant times something governed with the Hausdorff dimension. So yes, maybe you can also compute how much you are decreasing in each iteration to get something that you want to attain.
Okay, that's cool. Thank you.
Welcome.
Very nice. Any other questions from the audience? If not, I would stop the recording here and go towards the private question session if there are any. So Thank you once again for being with us today, Ivan.
Thank you. Thank you too.